Imagine a ship, not a shuttle, not a capsule, a world. A sealed civilization carrying thousands of people through the emptiest, coldest, most unforgiving environment in existence. No port to dock at, no supply line, no rescue mission. Every breath recycled, every drop of water recovered, every calorie grown from soil that has never touched rain. This is the colony ship. Humanity's most ambitious idea for survival beyond Earth. But here is the question nobody wants to answer honestly. How long could it actually last? Not the hull, not the engines, the living system inside, the air, the food, the people. The answer's not a number. It is a countdown shaped by every system that could quietly, invisibly fail. And eventually one of them will. If you find this kind of deep science fascinating, take a second to like and subscribe. It helps more than you think, and we never take it for granted. Also, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, are you comfortable? Let's begin. There is a difference between flying through space and living in it. It is a difference so fundamental that most people never stop to consider it. Because every spacecraft humanity has ever constructed belongs entirely to the first category. We fly through space, we visit it, we pass through it and come home. The longest any single human being has ever lived continuously off the surface of Earth is 437 days. That was cosmonaut Valery Polyakov aboard the Russian space station Mir in 1994 and 1995. He survived. He returned to Earth under his own power. And every single day of that record-breaking mission, his survival depended on cargo ships launched from the planet below. His food was packed in Russian warehouses. His water was loaded into supply vehicles in Kazakhstan. His oxygen system was maintained with the replacement parts manufactured in factories that breathed the same atmosphere he was slowly leaving behind. He was not living in space. He was camping in it, sustained entirely by a lifeline stretching back to the ground. The International Space Station, the largest and most complex structure ever assembled in orbit, has been continuously inhabited since the year 2000. More than 25 years of permanent human presence beyond the atmosphere. That sounds extraordinary, and it genuinely is. But the station is not self-sufficient, not even close. Every few months, a cargo vehicle arrives carrying water, food, spare parts, clothing, medical supplies, experiment hardware, and replacement components for the systems keeping the crew alive. Without those deliveries, the station would become uninhabitable within months. The oxygen generation system depends on water electrolysis, which depends on water, which is recycled but not perfectly. The carbon dioxide scrubbers depend on chemical canisters and mechanical filters that wear out and must be replaced. The food is pre-packaged on Earth. The small quantities of lettuce and radishes grown aboard in NASA's veggie growth chambers represent a scientific proof of concept, not a nutritional strategy. If you removed the supply chain tomorrow and told the crew they were on their own, the station would transition from an outpost to a crisis within weeks. The ISS is a lifeboat with a phone line to shore. Cut that line, and the countdown begins. Now imagine cutting it permanently. Not for weeks. Not for a mission duration measured in months. Forever. A colony ship is not a bigger version of the space station. It is not a shuttle with more seats, or a capsule stretched out for a longer trip. A colony ship is a fundamentally different category of object. It is a sealed, self-sustaining artificial world designed to keep an entire human population alive for years, decades, or even centuries without any contact with Earth, without any resupply mission, without any external rescue, and without any planetary surface to fall back on. Everything the colony needs to survive must either be inside the hull at the moment of departure, or the ship must be capable of producing it from the materials it carries. There is no margin for assumptions about future deliveries. There is no backup. There is no second chance. The nearest help will be light years behind, and light years at any speed humanity can currently achieve means generations of travel time. That single distinction transforms the engineering problem entirely. A spacecraft carries passengers, a colony ship carries a civilization. And the question of how long it could survive in deep space is really the question of how long a sealed civilization can keep itself alive inside a machine with nothing outside but vacuum, radiation, and cold. The answer starts with air. A human being inhales roughly 11,000 liters of air per day. Each breath draws in oxygen and pushes out carbon dioxide. In a sealed environment with no ventilation to the outside, this exchange becomes lethal surprisingly fast. The carbon dioxide you exhale does not vanish, it accumulates. At concentrations above roughly 5%, it causes headaches, dizziness, impaired judgment, and confusion. Above roughly 10%, it causes unconsciousness. Above 15%, it kills. In a small sealed room, a single person could reach dangerous carbon dioxide levels within hours. On the International Space Station, this is managed through a combination of chemical absorption and electrochemical recycling. The station uses a process called the Sabatier reaction, in which carbon dioxide is combined with hydrogen over a nickel catalyst to produce methane and water. The water produced is then fed into an electrolysis unit that splits it into hydrogen and oxygen. The oxygen goes back into the cabin atmosphere. The hydrogen feeds back into the Sabatier reactor for another cycle. The methane, which currently has no use aboard the station, is vented into space as waste. On paper, this creates something approaching a closed loop. Carbon dioxide in, oxygen out, water as the medium, hydrogen as the carrier. In practice, the loop leaks. Some hydrogen escapes. Some water is lost to inefficiencies in the system. The chemical reactions are never 100% efficient, and they never will be. The catalysts degrade over time. The filters that remove contaminants from the airstream clog and must be replaced. The electrolysis cells corrode, and the entire chain requires a constant supply of electrical power. Without electricity, every pump stops, every reaction halts, and the atmosphere inside the vessel begins its slow slide toward unbreathable. A colony ship would need to run this cycle, or something like it, continuously for the full duration of its voyage. Not for the 14-day stretch of a shuttle mission. Not for 6 months aboard the station. For decades, possibly for centuries. Every inefficiency compounds over that timescale. Every gram of gas lost through a microscopic seal leak, every milligram of catalyst consumed, every fraction of a percent of water that escapes the recovery loop represents a tiny debt against the ship's finite reserves. On Earth, those debts are invisible. In deep space, they accumulate into an existential threat. The European Space Agency recognized this problem decades ago and began a program called MELISSA, the Microecological Life Support System Alternative, in 1989. Rather than relying entirely on chemistry and mechanical systems, MELISSA integrates biology into the loop. The concept uses compartments of specialized bacteria, photosynthetic algae, and higher plants arranged in a chain that breaks down human waste. converts carbon dioxide into oxygen through photosynthesis, purifies water through biological filtration, and produces edible biomass as a food supplement. The pilot plant at the Autonomous University of Barcelona has been progressively closing this biological loop over more than 20 years of operation, and a 2025 conference paper documented continued progress in connecting its compartments and demonstrating stable operation. But full closure of the loop, meaning a system that can sustain a human crew indefinitely without any external input, has not yet been achieved even on the ground. Scaling such a system to support thousands of people aboard a vessel moving through interstellar space introduces challenges in contamination control, microbial drift, and system stability that remain unsolved. And that is just the air. The next survival layer is water. And in some respects, water is even harder. Every person aboard a colony ship requires roughly 1 gallon of water per day for drinking, food preparation, and basic hygiene. A crew of 1,000 would consume 1,000 gallons daily. 10,000 people would need 10,000 gallons. Over a single year, that adds up to millions of gallons. The ship cannot possibly carry enough water to supply that volume for decades of travel. It must recycle virtually everything. NASA achieved a landmark in 2023 when the environmental control and life support system aboard the ISS demonstrated a water recovery rate of 98%. That number represents an extraordinary engineering achievement. The system recovers water from cabin humidity, from sweat captured by dehumidifiers, and from urine processed through vacuum distillation and brine extraction. The output is cleaner than most municipal tap water on Earth. Christopher Brown, a member of the Johnson Space Center team managing the system, described the milestone in direct terms. If you launch with 100 pounds of water, he explained, you lose 2 pounds and the other 98 keeps going around and around. But consider what that 2% loss means across time. Start with 100 units of water. After one cycle, you have 98. After 10 cycles, you have roughly 82. After 50 cycles, you have roughly 36. The mathematics of compound loss is unforgiving. Even a 98% recovery rate, sustained over years without replenishment, drains the system towards zero. A colony ship would need to push that number far closer to 99.9%, and even then find some way to recover or produce the fraction that inevitably escapes. In deep space, there are no comets to intercept for ice. There are no moons to mine. Every molecule of water the ship will ever possess must be aboard at departure or synthesized from stored hydrogen and oxygen reserves that are themselves finite. And water is not only for drinking. It is the working fluid of the oxygen generation system. It is the medium for growing hydroponic crops. It is used as coolant for the reactor and electronics. It can serve as radiation shielding. Every litre used for one purpose is a litre unavailable for another, and the competition between these uses grows sharper as any loss accumulates. The shadow of Biosphere 2 falls across this entire problem. In September of 1991, 8 people sealed themselves inside a 3-acre glass and steel facility in the Arizona desert. Biosphere 2 was designed to be a completely self-sustaining ecosystem. A miniature Earth containing a rainforest, a desert, a savanna, wetlands, a small ocean, and an agricultural zone. The project aimed to demonstrate that humans could live inside a closed system, producing all their own food, recycling all their own water, and maintaining a breathable atmosphere with no external inputs. It was the most ambitious closed ecosystem experiment ever attempted on this planet. The atmosphere failed first. Over the course of the mission, oxygen levels inside the structure dropped from a normal 21% to a dangerously low 14.2%. That concentration is roughly equivalent to breathing at an altitude of 14,000 feet. The crew became fatigued, mentally foggy, and physically weakened. They struggled to perform the manual labor required to maintain the agricultural systems, which created a cascading effect. Less labor meant fewer crops tended, which meant less food, which meant less energy for labor. The cause was eventually traced to two mechanisms that no one had adequately predicted. Soil microbes in the agricultural and rainforest biomes were consuming oxygen at a far higher rate than the plants could replace it, because the soils had been enriched with too much organic material. Simultaneously, the facility's unsealed concrete was undergoing a slow chemical reaction with carbon dioxide in the air, binding carbon and trapping oxygen in calcium carbonate. The structure itself was eating the atmosphere. The crew survived the full 2 years, but only because supplemental oxygen was pumped in from outside, breaking the closed-loop seal that was the entire point of the experiment. Crops failed due to unexpectedly cloudy weather that limited sunlight. Pest species, particularly cockroaches, mites, and invasive ant colonies, exploded in population while their natural predators died off. The crew was chronically hungry throughout the mission. Biosphere 2 sat on the surface of Earth. It had gravity, it had direct sunlight, it had stable external temperatures. It experienced none of the vibration, radiation, vacuum exposure, or micrometeorite bombardment of space. It covered 3 acres of Arizona desert, and it could not sustain 8 people for 2 years without outside intervention. A colony ship would need to accomplish what Biosphere 2 could not, at a far larger scale, in a far more hostile environment, for far longer with absolutely no door to open for help. Before food even enters the conversation, there is an even more fundamental requirement: temperature and pressure, and both are at war with the environment outside. Space is cold. Not cold the way a winter night is cold. Cold at a level that has no equivalent in human experience. The background temperature of the universe is approximately 2.7 Kelvin, roughly minus 270 degrees Celsius. At that temperature, unprotected human tissue freezes solid in seconds. Exposed water turns to ice almost instantly. Metals become brittle, lubricants solidify, seals contract and crack. The colony ship must maintain an internal temperature somewhere between roughly 18 and 25 degrees Celsius at all times, everywhere inside the habitat. That means continuously generating heat and distributing it evenly through corridors, living spaces, agricultural bays, water systems, and equipment rooms. But it also means rejecting excess heat. Every machine aboard produces waste heat. The reactor produces enormous quantities of it. Human bodies produce it. Lighting systems produce it. Without a way to dump that excess thermal energy into space, the interior of the ship would overheat just as lethally as it would freeze. On Earth, heat dissipation is simple. You open a window, you run a fan. Convection carries warmth into the atmosphere. In space, there is no atmosphere. The only way to shed heat is through radiation, using large panels that emit infrared energy into the void. Those radiator panels must be exposed to space, which means they're also exposed to micrometeorite impacts, cosmic ray degradation, and thermal cycling. Over decades, their emissive coatings degrade, their surfaces erode, their efficiency drops, and replacing or repairing exterior radiator surfaces requires extravehicular activity. Spacewalks in conditions where a single punctured suit means death. Pressure is the other half of this equation. The ship's atmosphere must be maintained at roughly 1 standard atmosphere, the same pressure found at sea level on Earth. Outside the hull, the pressure is 0. That differential is what keeps the crew alive, and it is also what constantly tries to tear the ship apart. Every square meter of hull surface bears the force of over 10,000 kilograms pushing outward against vacuum. Every seal, every window, every hatch, every joint between structural panels must withstand that force continuously for the entire duration of the voyage. A crack in a pressure vessel does not heal. It grows, slowly, invisibly, under the relentless outward push of the atmosphere inside. Submarines offer the closest Earth-based analogy. They operate under extreme pressure differentials, maintain sealed atmospheres, recycle air, and keep crews alive in isolation for months at a time. The longest submarine patrols run roughly 90 days, and those submarines return to port for extensive maintenance after every deployment. Their hulls are inspected, their seals are replaced, their systems are overhauled by shore-based teams with access to an entire industrial supply chain. A colony ship gets no such overhaul. Its hull must hold pressure not for 90 days, but for decades or centuries, and the only maintenance crew available is the population living inside it. Then there is food, and food may be the most fragile link in the chain. Pre-packaged food degrades. NASA research on long-duration storage has documented that nutritional content declines significantly within 3 to 5 years. Vitamins break down, fats oxidize and go rancid, textures deteriorate, colors fade. After several years, many stored foods retain enough calories but lose the micronutrients essential for long-term health. Vitamin deficiencies that would be trivial to correct on Earth. A simple supplement, a fresh orange, become dangerous aboard a vessel with no pharmacy resupply. A colony ship lasting decades cannot depend on stored rations. It must grow its own food. Space agriculture is real, but it is in its infancy. The veggie growth system on the ISS has successfully cultivated lettuce, radishes, chili peppers, and several other small crops in compact growth chambers using LED lighting and a porous clay substrate. Astronauts have eaten space-grown salads and reported that the experience of tending living plants provided significant psychological benefit. A finding confirmed by a recent NASA-supported study of 27 long-duration crew members who described crop growth tasks as enjoyable, engaging, and meaningful. But the quantities produced are tiny. A few leaves per cycle, a handful of peppers over months. The distance between growing a garnish and feeding a civilization is measured not in engineering refinements, but in orders of magnitude. A colony ship would need dedicated agricultural decks large enough to produce the full caloric and nutritional needs of its population. Wheat, rice, soybeans, potatoes, leafy greens, legumes, and likely insect or aquaculture protein would all need continuous cultivation under artificial light, fed by recycled water and composted waste. The energy cost of lighting alone would be staggering. Photosynthesis requires specific wavelengths and intensities of light. Providing that light artificially for hectares of growing area demands enormous, sustained electrical output from the ship's power system. And crops grown in altered gravity environments behave differently. ISS experiments have shown that space-grown lettuce contains reduced levels of calcium, potassium, phosphorus, and other essential minerals compared to Earth-grown controls. The reasons are still being investigated, but microgravity appears to affect how roots absorb nutrients and how fluids move through plant tissue. If the colony ship generates artificial gravity through rotation, some of these problems may be reduced. But rotation introduces structural stresses, bearing wear, and Coriolis effects on fluid systems that create their own category of engineering challenges. There is no recovery from a major crop failure aboard a colony ship. A blight, an unexpected pest, a contamination of the soil ecosystem, or a sustained failure of the grow lights would not mean a disappointing season. It would mean starvation. And unlike a farmer on Earth who can purchase grain from a neighboring region while replanting, a colony ship has no neighbor. Its agricultural system is the only source of food in existence. Redundancy helps, but redundancy costs space, energy, and resources, all of which are finite. And then there is waste. Every living organism aboard the ship produces waste. Human waste, agricultural waste, chemical byproducts from the air and water recycling systems, degraded filters, worn-out components, spoiled food, dead planet matter. On Earth, waste is someone else's problem. You flush it, bag it, or send it to a facility down the road. On a colony ship, there is no down the road. Every atom of waste is an atom that was once part of the supply chain. If it is not recovered, processed, and returned to the cycle, it represents a permanent loss. Human waste must be broken down into its component chemicals and reintegrated into the agricultural system as nutrients and into the water system as recoverable liquid. This is not just an engineering problem, it is a biological one. The microbial communities that break down waste in composting systems are themselves living organisms with their own requirements for temperature, moisture, and chemical balance. If those microbial communities shift, die off, or become contaminated with pathogenic organisms, the entire waste processing chain fails. And a failed waste chain means both a loss of recyclable nutrients and a growing accumulation of untreated biological material inside a sealed vessel, which is a direct path to disease. Every one of these challenges, air, water, food, temperature, pressure, waste, has been studied. None has been solved at the scale and duration a colony ship would require. Beneath every one of these systems sits the foundation that makes all of them possible: power. Without a continuous supply of electricity, nothing aboard the ship functions. The air recyclers stop, the water purifiers shut down, the grow lights go dark, the temperature regulation system fails. The cabin atmosphere begins cooling toward the minus 270 degrees Celsius of the vacuum outside. Power is not one system among many aboard a colony ship. It is the system that enables every other system to exist. In deep space, far from any star, solar panels are useless. The intensity of sunlight drops with the square of the distance from the source. Beyond the orbit of Jupiter, solar energy is already too faint to be practical. In interstellar space, it is effectively zero. The ship must carry its own energy source, and that source must last for the entire duration of the voyage. The most proven long-duration power technology in space is the radioisotope thermoelectric generator. The Voyager probes, launched in 1977, are still operating nearly 50 years later on the power of their onboard generators, which convert heat from the radioactive decay of plutonium-238 into electricity through the Seebeck effect. It is an extraordinary demonstration of longevity, but each Voyager generator produced only about 157 watts at launch. 3 generators per spacecraft provided a combined output of roughly 470 watts. That is enough to power a few household light bulbs. A colony ship with thousands of inhabitants, agricultural systems, life support equipment, and manufacturing capability would require millions of watts sustained for decades or centuries. The only realistic option at that scale is a nuclear fission reactor, and possibly a fusion reactor if that technology matures sufficiently. A fission reactor can produce megawatts of continuous power from a relatively compact fuel source. Uranium fuel assemblies can operate for years before requiring replacement. But a reactor is not a sealed battery. It is an active, complex machine. It requires coolant loops, control rod mechanisms, neutron moderators, containment shielding, heat exchangers, turbines or thermoelectric converters, and a waste heat rejection system. Its internal components are bombarded by the very neutrons it produces, causing embrittlement and activation of the structural materials over time. The reactor vessel itself becomes radioactive and must eventually be serviced or replaced. No fission reactor on Earth has operated continuously for more than roughly 60 years, and every one of those reactors had access to an entire industrial civilization for maintenance, refueling, and component manufacturing. A colony ship reactor would need to operate for the full duration of the voyage, with only the tools, fuel, and spare parts carried aboard. If the reactor fails and cannot be restarted or replaced, every other system aboard the ship fails with it. Power is not a subsystem, it is the heartbeat. And here is the dimension of this problem that becomes clear only when you look at all of these systems together, rather than one at a time. They do not operate independently. They form a web of mutual dependency so tight that pulling on any single thread sends vibrations through the entire structure. The air recycler needs electricity from the reactor. The reactor needs cooling water from the water system. The water system needs pumps powered by the reactor. The food system needs light powered by the reactor and water supplied by the recycler. The recycler needs filters that must be manufactured aboard the ship. Manufacturing needs tools, which need metal, which needs a forge, which needs power from the reactor, which needs cooling from the water system. Every loop connects to every other loop. Every dependency creates a vulnerability. And every vulnerability is a point where the entire system can begin to unravel. This is what separates a colony ship from every other engineering project in human history. A bridge has one function, a power plant has one function, an airplane has one function. A colony ship must simultaneously be a power plant, a farm, a water treatment facility, a hospital, a factory, a waste processing center, and a habitat, all sealed inside a single pressure vessel, hurtling through vacuum at unimaginable distance from any help. It is not a machine with a purpose. It is an ecosystem with a pulse. On Earth, we are shielded from this reality by the planet itself. If the power grid fails, the atmosphere does not vanish. If the water system breaks, rain still falls. If a harvest fails, grain can be imported from another continent. Earth's biosphere, 4.5 billion years in the making, is the ultimate redundancy. It has absorbed asteroid impacts, supervolcanic eruptions, and ice ages lasting millions of years and continued to support life. A colony ship has no such buffer. It is an artificial biosphere assembled from components, maintained by the same fragile species it is designed to protect, and operating inside an environment that offers no forgiveness for error, no grace period for recovery, and no second chance if a critical system crosses the line from damaged to destroyed. The ship does not need to be perfect, but it needs to stay functional. And it needs to stay functional not for a mission measured in days or months, but for a voyage that could last longer than any single institution in human history has ever survived. The first months, perhaps even the first few years, might proceed almost as designed. The crew would breathe recycled air, drink purified water, eat crops grown under banks of artificial light, and live inside a pressurized habitat held at a comfortable temperature by the steady output of a nuclear reactor. The engineering would hold, the systems would perform. Life inside the ship might even feel routine, but time does not forgive. And the deeper the ship travels into the emptiness between stars, the farther it moves from any possibility of rescue or resupply, a second layer of threat begins pressing against the hull. Not the internal systems straining to keep up with demand, something coming from outside, the radiation that never stops, the particles that never miss, the cold that never relents, the universe doing what it does to every object that dares to exist within it, wearing it down, atom by atom, year by year. The systems inside the colony ship are fighting to keep a population alive. The universe outside is fighting to make that impossible. And the universe is patient in a way that no human engineer can match. Everything discussed up to this point concerned the challenge of maintaining life support within the hull. Air recycling, water recovery, food production, power generation, temperature regulation, waste processing. Each one is an engineering problem that can, at least in theory, be designed for. The components can be specified. The redundancies can be built. The failure modes can be studied and mitigated. But there is a second category of threat that no amount of internal engineering can fully eliminate, because it comes from the environment itself. Space is not simply empty. It is actively hostile, and its hostility operates on timescales that turn even the most durable materials into liabilities. The first and most pervasive of these external threats is radiation. Not the kind that comes from a nuclear reactor or a medical scanner. The kind that comes from everywhere, all the time, with no off switch and no shelter. Galactic cosmic rays are the ghosts of dead stars. When a massive star reaches the end of its life and collapses in a supernova, the explosion accelerates atomic nuclei to velocities approaching the speed of light. These particles, stripped of their electrons, hurtle through the galaxy in every direction. They consist mostly of protons, roughly 87%, with the remainder being helium nuclei, heavier ions from elements like carbon, oxygen, silicon, and iron, and a small fraction of electrons. They carry enormous energy. A single galactic cosmic ray particle can possess the kinetic energy of a fast-pitch baseball, compressed into a space smaller than an atom. On Earth, you never feel them. The planet's magnetic field deflects the lower energy particles outward. The atmosphere absorbs much of what gets through, producing harmless secondary particles that shower down as background radiation at ground level. The combination of magnetosphere and atmosphere provides shielding equivalent to roughly 1,000 grams per square centimeter of material overhead. It is an invisible fortress, and every living thing on Earth has evolved inside it. A colony ship in deep space has neither a planetary magnetic field nor an atmosphere. The crew is exposed to the full galactic cosmic ray flux, unfiltered and undiminished, for every second of the voyage. And this is where the physics becomes genuinely frightening. The heaviest galactic cosmic ray particles, known as HZE ions, for high atomic number and high energy, are the most dangerous. These are nuclei of heavy elements like iron, traveling at close to the speed of light. When an iron nucleus at that velocity strikes a sheet of aluminum hull plating, it does not simply stop, it punches through. And as it passes through the metal, it shatters the nuclei of aluminum atoms in its path, producing a spray of secondary particles, neutrons, protons, lighter ions, and gamma rays that fan outward in a cone behind the impact point. This secondary shower is itself biologically damaging. In many cases, the secondary radiation produced inside the shielding is more harmful than the original particle would have been if it had simply passed through tissue cleanly. This is the cruel paradox of radiation shielding in space. Adding more aluminum does not always make the crew safer. Beyond a certain thickness, the aluminum generates more secondary radiation than it absorbs. NASA research has confirmed this effect repeatedly. A 2026 discussion at a University of California symposium on deep space radiation noted that galactic cosmic rays at giga-electron-volt energies can barrel through hundreds of meters of conventional shielding, and that any spacecraft venturing beyond Earth's magnetosphere faces a radiation challenge that current technology cannot fully solve. Hydrogen-rich materials perform better than metals because hydrogen nuclei, being the lightest possible atoms, produce fewer and less energetic secondary particles when struck. Water, polyethylene, and other hydrogen-dense substances are more effective per unit mass than aluminum or steel. Some colony ship designs propose surrounding the habitat with thick water walls that serve simultaneously as radiation shielding and as a water reservoir. This is a clever dual-use solution, but it is also a massive one. Effective shielding against galactic cosmic rays using water would require walls several meters thick. The mass involved is enormous. Every kilogram of shielding is a kilogram that must be launched, accelerated, and carried for the entire voyage. Even with the best passive shielding available, galactic cosmic ray exposure aboard a colony ship would substantially exceed the levels that astronauts experience on the International Space Station, which already sits partially within the protection of Earth's magnetic field. NASA has estimated that a round-trip Mars mission lasting roughly 2 to 3 years in deep space could expose astronauts to radiation doses approaching or exceeding current career exposure limits. A colony ship voyage lasting decades or centuries would accumulate doses that dwarf any mission profile ever seriously planned. The biological effects of that exposure are not immediate. They are not dramatic. They do not announce themselves with sirens or visible symptoms. They are silent and they are relentless. Cosmic ray particles passing through human tissue damage. DNA. A single HZE ion traversing a cell nucleus can shatter both strands of the DNA helix simultaneously, producing a type of damage called a double-strand break. The cell has mechanisms for repairing this damage, but the repair is imperfect. Sometimes the broken strands are rejoined incorrectly, producing mutations. Sometimes the damage is too severe to repair at all, and the cell either dies or begins dividing abnormally. Over time, unrepaired or misrepaired DNA damage accumulates. The result is an elevated lifetime risk of cancer, cataracts, cardiovascular disease, and central nervous system degeneration. Studies conducted using animal models exposed to simulated galactic cosmic ray environments at NASA's Space Radiation Laboratory have documented increased tumor incidence, measurable cognitive decline including impaired memory and spatial reasoning, and suppression of immune function. What makes galactic cosmic ray damage particularly insidious is that it cannot be fully mitigated by any known biological countermeasure. Antioxidants, dietary supplements, and pharmaceutical radioprotectors can reduce some categories of radiation damage, but are largely ineffective against the dense ionization tracks left by HZE particles. The damage these ions produce is qualitatively different from the damage caused by medical X-rays or gamma radiation. It is concentrated along narrow corridors through tissue, destroying clusters of cells in a pattern that the body's repair mechanisms are poorly equipped to handle. For a colony ship population spanning multiple generations, these effects compound in ways that have never been studied in living human populations. Children conceived and born aboard the ship would be exposed to elevated radiation from the moment of conception. Their developing tissues, which are far more sensitive to radiation damage than adult tissue, would accumulate mutations at a rate significantly above the terrestrial baseline. Over generations, the genetic burden on the population would grow. The colony's healthcare system would face rising rates of disease in a setting where medical resources are strictly finite and irreplaceable. But radiation does not limit its damage to human bodies. It strikes every living system aboard the ship. The seeds stored for future planting accumulate genetic damage in storage, and the crops grown from those seeds carry mutations that may reduce yield, alter nutritional content, or weaken resistance to pests and disease. Each successive generation of plants grown under elevated radiation drifts further from the carefully selected cultivars that were loaded at departure. The microbial cultures that form the backbone of the biological life support system, the bacteria that break down waste, the algae that produce oxygen, the nitrogen-fixing organisms that sustain the soil, are all living populations whose genomes are being altered by the same particles hitting the crew. Microbes reproduce rapidly, which means radiation-induced mutations propagate through their populations far faster than through the human population. A culture of photosynthetic algae could, over years of elevated exposure, drift toward strains that generate less oxygen than intended. The ship's biological infrastructure is not a machine that either works or does not. It is a living community under constant genetic assault, evolving in directions that no one chose and no one fully controls. Active shielding. Generating an artificial magnetic field around the ship to deflect charged particles the way Earth's magnetosphere does, has been proposed as an alternative. The concept is physically sound. A sufficiently powerful magnetic field would push galactic cosmic rays away from the habitat, but the engineering requirements are staggering. The field would need to be sustained over an enormous volume. The superconducting magnets required would demand significant power and cooling, and the field itself would need to be carefully shaped to avoid creating zones of concentrated radiation at its edges, regions where deflected particles pile up into intensified beams rather than being dispersed. No active shielding system has ever been tested at the scale required. The concept remains theoretical, and while theoretical solutions can become engineering realities given enough time and investment, a colony ship cannot wait for the technology to mature. It must launch with the shielding it has. Radiation is the constant. It never stops. It cannot be turned off. It penetrates the hull, passes through the shielding, and deposits its energy in the bodies of the crew and in the electronic systems they depend on, every hour of every day for the entire voyage. It is not a crisis. It is a condition, and it is only one of the threats pressing against the ship from outside. The second is impact. Interstellar space is often described as empty, and by terrestrial standards it is. But empty in space does not mean devoid of matter. The interstellar medium contains roughly 1 atom per cubic centimeter on average, mostly hydrogen, with traces of helium and tiny grains of dust, composed of silicates, carbon compounds, and ice. By everyday standards, this is a vacuum so extreme it makes the best laboratory vacuum on Earth look like fog. But a colony ship moving through this medium at any appreciable fraction of the speed of light is not standing still in a vacuum. It is moving through it, and relative velocity changes everything. At 10% of the speed of light, roughly 30,000 kilometers per second, a collision with a single grain of interstellar dust weighing 1 milligram would release energy equivalent to over 100 kilograms of high explosive from a particle smaller than a grain of sand. At the velocities required for interstellar travel within a human lifetime, even atoms of hydrogen become projectiles. Each impact deposits a tiny amount of energy into the whole surface. Individually, these impacts are negligible. Collectively, over years and decades, they produce a slow, invisible erosion of the forward-facing surfaces of the ship. The leading edge is being sandblasted at the atomic level by the very medium it is traveling through. Even at lower velocities, the kind achievable with current or near-future propulsion concepts, micrometeorites pose a sustained threat. These are fragments of ice, rock, metal, and carbonaceous material ranging in size from microscopic dust, smaller than a bacterium, to particles a few millimeters across. In the space between planetary systems, their density is far lower than in the debris-rich environment of a star's inner system, or the cluttered orbital zone around a planet. But they are not absent. Dust permeates the galaxy. It collects in the plane of the galactic disk. It streams outward from regions of active star formation. It lingers in the remnants of ancient supernovae. The colony ship cannot chart a course that avoids it entirely, because there is no region of the galaxy that is truly dust-free. And because the ship is traveling through this medium continuously, over decades, the probability of encountering particles large enough to cause meaningful structural damage increases steadily with every passing year. The standard defense against micrometeorite impacts is the Whipple shield, named after the astronomer Fred Whipple, who proposed the concept in 1947. A Whipple shield consists of 2 or more thin layers of material separated by a gap. When a high-velocity particle strikes the outer layer, both the particle and the portion of the shield it hits are vaporized or fragmented into a cloud of smaller, less energetic debris. This debris cloud spreads out as it crosses the gap, distributing its energy over a much larger area of the inner wall, which can then absorb the impact without being penetrated. Whipple shields are proven technology. They protect the International Space Station against orbital debris impacts at velocities up to roughly 7 kilometers per second. But they are not permanent. Every impact that the outer layer absorbs is an impact that degrades it. Over time, the bumper layer accumulates pitting, cratering, and material loss. Its ability to fragment incoming particles diminishes as its structural integrity decreases. And the inner wall, while protected by the expanding debris cloud, is not immune to damage either. Over decades, the cumulative effect of thousands of small impacts weakens both layers. Repairing or replacing Whipple shield panels on the exterior of a colony ship would require extravehicular activity. Spacewalks in interstellar space carry risks that make current ISS spacewalks look routine. There is no space station structure to anchor to. There is no rescue vehicle standing by. The ship is moving at high velocity through a medium that, as we have discussed, contains particles capable of puncturing a suit. A single micrometeorite strike to a suited crew member during a repair operation could be fatal, and the repairs themselves must be conducted using tools, materials, and spare panels that the ship carries in finite supply. The third external threat is material fatigue, and it is the most insidious because it requires no dramatic event. It is simply the consequence of time. Every material has a lifespan. Metals fatigue under repeated stress as dislocations in their crystal structure propagate into cracks. Polymers degrade under radiation exposure as high-energy particles break the long molecular chains that give them their flexibility, turning supple gaskets into brittle fragments. Rubber seals lose their elasticity as their molecular structure slowly cross-links and hardens. Adhesives weaken, lubricants break down into compounds that corrode the surfaces they were meant to protect. Welds develop microcracks as thermal cycling, the repeated expansion and contraction caused by temperature variations across the hull, stresses the joints between structural members. Glass and ceramic insulators, which seem permanent on Earth, become clouded and weakened by cumulative radiation damage as particles displace atoms from their crystalline lattice positions. None of this happens quickly. A well-designed structure made from high-quality materials and assembled with expert craftsmanship might function perfectly for a decade. It might function well for several decades, but the operative word is might. And decades is the minimum timescale for a colony ship voyage, not the maximum. No one has ever tested any structural material under the simultaneous assault of deep space radiation, vacuum, thermal cycling, and micrometeorite bombardment for a century. No one can say with certainty what happens to a titanium alloy hull plate after 80 years of continuous cosmic ray exposure combined with 10 million thermal cycles. The data does not exist because the experiment has never been run. Thermal cycling is particularly aggressive in space. The whole surface facing a star, even a distant one, absorbs radiant heat and warms. The surface facing deep space radiates heat and cools. As the ship rotates or changes orientation, different sections of the hull cycle between warmer and cooler temperatures. Each cycle expands and contracts the metal by microscopic amounts. One cycle does nothing. 10 cycles do nothing. 1,000,000 cycles, accumulated over decades, can propagate a crack from invisible to catastrophic. On Earth, bridges and aircraft are inspected regularly for fatigue cracks. The inspectors use ultrasonic testing, X-ray imaging, and visual examination to catch cracks before they grow to critical size. When damage is found, the affected section is repaired or replaced using materials sourced from the global manufacturing infrastructure. On a colony ship, the inspection must be conducted by the crew using whatever diagnostic tools they carried aboard, and the repair must be made with whatever materials they have left. There is no factory producing replacement hull plates. There is no specialist flying in from another facility. The crew is the maintenance team, the inspection service, and the materials supplier, all at once. The fourth external threat strikes at the nervous system of the ship itself. Electronics. Every computer, sensor, controller, communication system, navigation instrument, and automated process aboard the colony ship depends on electronic circuits. And those circuits are under continuous assault from the same galactic cosmic rays that threaten the crew's biology. When a high-energy particle strikes a semiconductor chip, it can deposit enough charge in a transistor to flip a bit, changing a 0 to a 1 or a 1 to a 0. This is called a single event upset, and it happens with measurable frequency in space. On the ISS, single event upsets occur regularly and are managed through error-correcting software, redundant systems, and radiation-hardened chip designs. But single event upsets are an acute problem. The chronic problem is cumulative dose. Over time, the total ionizing radiation absorbed by a semiconductor device changes its electrical characteristics. Threshold voltages shift, leakage currents increase, timing margins narrow. Eventually, the device stops functioning reliably. It does not fail in a single dramatic moment. It degrades, becoming less precise, less predictable, less trustworthy, until the systems that depend on it begin producing errors that cascade through the ship's operations. Radiation-hardened electronics exist, designed specifically to resist these effects. They are used in military satellites, deep space probes, and high radiation environments on Earth, but they are slower, more expensive, heavier, and less capable than their commercial counterparts. And even radiation-hardened devices have lifetime limits. They are designed to survive a specific total dose, after which their performance is no longer guaranteed. For a colony ship lasting decades or centuries, those lifetime limits would be reached and exceeded. The Voyager probes offer an instructive comparison. Launched in 1977, both spacecraft have been operating in deep space for nearly 50 years. Their electronics have survived far longer than most engineers expected, but the Voyager electronics are extraordinarily simple by modern standards. The onboard computers have roughly 69 kilobytes of memory. They run programs that were written in the 1970s using redundant architectures designed for graceful degradation. They have no high-resolution displays, no complex networking, no graphical interfaces, no machine learning systems. They are calculators with radios attached. A colony ship would require computing systems orders of magnitude more complex. Life support automation alone would demand real-time monitoring of atmospheric composition, pressure, temperature, and humidity across hundreds of separate compartments. Navigation would require tracking the ship's position and velocity relative to its destination with precision that must be maintained over decades of continuous computation. Agricultural monitoring would need to track soil chemistry, nutrient levels, moisture content, lighting cycles, and pest detection across growing areas large enough to feed thousands. Medical diagnostics, communications, environmental control, power management, manufacturing control, structural health monitoring, and thousands of other functions would all depend on integrated electronic systems that must operate reliably for far longer than any terrestrial computer has ever been asked to function. And they would be doing so while absorbing radiation doses that steadily erode their ability to process information accurately. A corrupted byte in a temperature sensor reading might go unnoticed for weeks. A drifting calibration in the atmospheric monitoring system might not trigger an alarm until the air quality has already deteriorated. The errors do not announce themselves. They accumulate in the margins, hidden until they converge. The ship could carry stockpiles of replacement boards, processors, and memory modules. It could maintain cold spares, identical backup units kept unpowered and shielded until needed. But even cold spares degrade under radiation exposure over long enough timescales. The shielding around them reduces the dose but does not eliminate it. And the manufacturing technology required to fabricate new semiconductor devices from raw materials aboard a moving vessel in deep space does not currently exist. The process that produces a modern chip is among the most complex and infrastructure-dependent manufacturing chains in all of industrial civilization. Reproducing it demands specialized conditions, equipment, and global supply networks that cannot be miniaturized, made portable, or carried aboard a vessel. The idea of reproducing this capability in a shipboard workshop is not merely difficult, it is a challenge that sits beyond the horizon of any current engineering roadmap. This is the dimension of the problem that makes electronics potentially the weakest link in the entire chain. Air can be recycled with relatively simple chemistry and biology. Water can be filtered and purified using methods that date back centuries. Food can be grown with soil, seeds, light, and knowledge that a single trained agronomist could carry in their head. But the electronic systems that coordinate, monitor, and control all of these functions depend on a manufacturing base so complex that no single facility on Earth can reproduce it alone. When the last replacement chip fails and the ship cannot fabricate a new one, the systems that depend on it do not switch to a manual backup. In many cases, there is no manual backup. The automated process was the only process, and when it stops, the function it served stops with it. There is a fifth threat that becomes relevant at the highest velocities. At speeds above roughly 5% of the speed of light, the interstellar medium itself becomes a weapon. Hydrogen atoms, which are effectively stationary relative to the galaxy, strike the forward surface of the ship at relative velocities measured in tens of thousands of kilometers per second. At those speeds, each hydrogen atom carries enough kinetic energy to act as a miniature projectile, sputtering atoms off the whole surface on impact. The process is called sputtering erosion, and it operates continuously, invisibly, and cumulatively. The ship's forward hull is being ablated one atomic layer at a time. Over a voyage lasting decades at high velocity, the total erosion could measure in millimeters or more, depending on the ship's speed and the density of the interstellar medium along its path. This may sound trivial. A few millimeters off a hole that might be centimeters or even meters thick. But that erosion is not evenly distributed. It concentrates on surface features, edges, sensor housings, antenna mounts, and any protrusion that catches the oncoming particle stream. Critical external components that are difficult or impossible to repair from inside the ship are the first to suffer. And sputtering erosion interacts with the other degradation processes already described. A hull surface weakened by micrometeorite pitting erodes faster under particle bombardment. A structural joint already stressed by thermal cycling cracks more readily when its surface layers have been thinned by sputtering. A Whipple shield panel already degraded by decades of small impacts offers less protection when its thickness has been reduced by atomic scale ablation. The threats do not simply add together, they multiply each other. This is the principle that dominates the long-term survival picture for a colony ship, and it is the principle that makes simplistic estimates of whole lifespan dangerously misleading. No single external threat would destroy the ship quickly. Radiation alone would not kill the crew in a year. A single micrometeorite impact would not breach the hull. One thermal cycle would not crack a weld. One bit flip would not crash the navigation system. But these processes do not operate alone. They operate simultaneously, continuously, and cumulatively. Each one accelerates the others. Each one exploits the damage the others have already done. A hole designed to last a century in a single threat environment might last only 50 years when radiation embrittlement, micrometeorite pitting, thermal cycling, and sputtering erosion are all acting on it at once. An electronic system rated for a 30-year radiation dose might fail in 15 if single event upsets are corrupting the error correction routines that would normally compensate for cumulative dose effects. A Whipple shield designed to absorb 10,000 impacts might fail after 6,000 if the impacts are landing on surfaces already thinned by erosion and weakened by radiation damage to their polymer bonding layers. The ship launched as a fortress. Its hull was thick. Its shielding was dense. Its electronics were hardened. Its seals were tight. Everything was new, tested, certified, and strong. But from the moment it left the protection of the solar magnetic field and entered the open ocean of interstellar space, every one of those protections began to degrade. Not in a way the crew would notice immediately, not in a way that alarms would catch in the first year or even the first decade, but steadily, relentlessly, and irreversibly. The universe does not attack a colony ship the way a storm attacks a house. It does not strike suddenly and pass. It presses, continuously, from every direction, with radiation that never stops, particles that never miss, temperatures that never relent, and a patience that outlasts any material ever forged. The ship can resist. It can endure. It can repair some of what is damaged and compensate for some of what is lost. But it cannot win a war of attrition against the environment it exists within. It can only delay the outcome. And that is exactly where the most critical question in this entire story emerges. Because everything described so far, every seal that cracks, every chip that degrades, every shield panel that thins, every hull surface that erodes, can theoretically be repaired. If the crew has the tools, if they have the materials, if they have the spare parts, if they have the knowledge, if they have the manufacturing capacity to build replacements for the things that cannot be stored, the ship does not die from damage. It dies from the inability to fix the damage faster than it accumulates. And the question of how long a colony ship can survive ultimately comes down to one deceptively simple problem that turns out to be the hardest engineering challenge humanity has ever imagined. Not how to build the ship, not how to launch it, not how to power it or shield it or feed the people inside it, but how to keep fixing it. How to repair the machines that repair the machines, how to replace the irreplaceable, and what happens to the people aboard when the answer to that question finally becomes nothing. There is a question hiding inside every engineering diagram of every colony ship ever proposed. It is not about thrust or fuel or trajectory. It is not about how many people the ship can carry or how fast it can travel. It is a question so basic that it almost sounds naive. What happens when something breaks? On Earth, the answer is obvious. You fix it. You order a replacement part. You call a specialist. You drive to a hardware store. You contact the manufacturer. The entire apparatus of industrial civilization exists, in a sense, to answer that question. Something breaks, and the global network of mines, refineries, factories, logistics chains, and skilled labor produces a replacement and delivers it to wherever it is needed. This system is so pervasive, so deeply embedded in daily life that most people never consciously think about it. The light switch works. The pipe gets repaired. The car part arrives in 2 days. The system is invisible because it is everywhere. On a colony ship, the system is gone. All of it. Every factory, every warehouse, every supply chain, every specialist who spent 20 years learning a single manufacturing process. The ship carries what it carries, and when something breaks, the only resources available for fixing it are the materials, tools, knowledge, and people already aboard. There is no phone call to make. There is no delivery coming. There is no next town over the horizon. There is only what the ship has and what the crew can do with it. This is the problem that separates a colony ship from every other engineering challenge in history. And it is the problem that ultimately determines how long the ship can survive. Start with the most straightforward layer. Spare parts. Every pump aboard the ship has bearings that wear. Every valve has seals that harden and crack. Every filter clogs. Every circuit board accumulates radiation damage. Every mechanical actuator has a fatigue life measured in cycles. Every light bulb burns out. These are not failures of design, they are facts of material science. Moving parts wear, static parts degrade, nothing lasts forever, and in the hostile environment of deep space, nothing lasts as long as it would on Earth. The obvious solution is to carry spares. Load the ship with replacement pumps, backup circuit boards, extra seals, reserve filters, and duplicate assemblies for every critical system. NASA has studied this approach extensively in the context of long-duration Mars missions. The research concluded that achieving what engineers call ultra-reliable life support, a system with an acceptably low probability of mission-ending failure over multi-year durations, requires carrying spare components with a total mass approximately equal to the mass of the original system. In other words, to ensure reliability over a long mission, you essentially bring 2 of everything. For a 6-month Mars transit, this is feasible. The mass penalty is large but manageable within the constraints of available launch vehicles. For a colony ship lasting decades or centuries, the math collapses. Carrying 2 of everything means doubling the ship's already enormous mass. Carrying 3 of everything, which is what a century-long voyage might demand, means tripling it. And tripling the mass means tripling the fuel required to accelerate it, tripling the structural load on the frame, tripling the cost, and tripling the number of things that can themselves break and need their own spares. There is also the question of prediction. Which components will fail first? In what order? The ship's designers must decide before launch how many of each spare to carry based on estimated failure rates for every component aboard. If they overestimate the lifespan of a pump seal by a factor of 2, the ship runs out of replacement seals in half the expected time. If they underestimate the durability of a circuit board, they waste precious mass carrying spares that sit unused while some other component runs short. The inventory must be nearly perfect in its predictions about the future, and it must be managed with flawless discipline for decades. A single misplaced crate, a single miscounted stock item, a single inventory record corrupted by a radiation-induced bit flip in the database could leave the crew without a critical part they were certain they still had. There is also a subtler problem. Spare parts are not immortal. A replacement circuit board sitting in a shielded storage locker is still being slowly degraded by the galactic cosmic rays penetrating the hull. A rubber seal stored in vacuum-sealed packaging is still aging at the molecular level. A backup pump motor sitting on a shelf for 40 years may not function when finally installed Because its lubricants have dried, its windings have become brittle, or its insulation has degraded beyond its tolerance. Stored spares buy time. They do not buy independence, they delay failure. They do not prevent it. The only way to escape this trap is manufacturing. If the ship can build replacement parts from raw materials, it is no longer limited by the size of its inventory. A broken pump bearing can be machined from bar stock. A failed seal can be molded from polymer feedstock. A burned out heating element can be wound from wire. The ship transitions from a vessel carrying a fixed supply of components to a vessel carrying the capability to produce components on demand. This is the difference between a packed suitcase and a workshop. One runs out. The other, in theory, does not. But manufacturing aboard a colony ship introduces a recursion problem so deep that it constitutes, in the opinion of many researchers, the single hardest unsolved challenge in interstellar mission design. A machine shop needs machine tools: lathes, mills, grinders, presses, welders, and cutting equipment. Those tools are themselves machines made of parts that wear. The lathe that machines a replacement bearing will itself eventually need new bearings. The mill that cuts a new valve body will eventually need a new cutting head. The welder that joins hole patches will eventually need new electrodes, new gas supplies, and new power cables. Each tool in the shop is subject to the same wear and degradation as the components it exists to replace. So the shop must also be able to repair its own tools. This requires a second tier of capability: tools to fix tools, jigs, fixtures, measurement instruments, and raw materials suitable for fabricating machine components. But those second-tier tools also degrade. The precision measuring instruments that ensure a replacement part meets its specifications are themselves subject to calibration drift, mechanical wear, and radiation damage. The jigs that hold workpieces in alignment slowly warp. The fixtures that clamp raw material in place develop play in their mechanisms. This creates a dependency chain that extends downward through every level of the manufacturing hierarchy. The ship needs machines to make parts. It needs machines to fix the machines that make parts. It needs tools to service the machines that fix the machines that make parts. At every level, the tools are subject to the same degradation as the things they repair. And at some level, the chain must terminate in something irreducible, a component or a capability that cannot itself be manufactured aboard the ship. Consider a concrete example. The water recycling system uses a pump with a ceramic-coated impeller. After 15 years of continuous operation, the impeller's coating wears through and the pump loses efficiency. The ship's machine shop can fabricate a new impeller from metal stock, but cannot reproduce the ceramic coating because the plasma spray equipment required for that process was too heavy and too specialized to carry aboard. The crew installs an uncoated metal impeller instead. It works, but it corrodes faster in contact with the chemically aggressive recycled water. Instead of lasting 15 years, the replacement lasts 6. The next replacement lasts 5. The one after that lasts 4. Each iteration degrades faster because the substitution moved the component further from its design specification. The pump still works. The water still cycles. But the maintenance interval has shortened. The crew spends more time on pump repairs, and the metal stock is consumed at an accelerating rate. Nothing broke catastrophically. The system simply became more expensive to sustain, measured in time, labor, and irreplaceable material with each passing cycle. Multiply that pattern across hundreds of systems. each with its own substitution compromises and accelerating maintenance demands, and the picture of long-term survival begins to sharpen. That terminus in the dependency chain, the irreducible component the ship cannot fabricate, is where the survival clock truly starts. The clearest example is semiconductors. Modern life support systems, navigation computers, communication equipment, power management controllers, agricultural monitoring sensors, and medical diagnostic devices all depend on integrated circuits. These chips are manufactured on Earth using a process so complex and so dependent on specialized infrastructure that it represents one of the most concentrated expressions of industrial civilization ever created. A modern semiconductor fabrication facility costs tens of billions of dollars to build. It requires clean rooms where the air is filtered to remove particles smaller than 10 nanometers. It uses photolithography machines that project circuit patterns onto silicon wafers using extreme ultraviolet light with wavelengths of 13.5 nanometers. It requires hundreds of specialized chemicals, gases, and ultra-pure materials sourced from suppliers around the world. The entire process, from raw silicon to finished chip, involves hundreds of individual steps, each requiring equipment that is itself the product of decades of engineering and refinement. No colony ship could carry a semiconductor fabrication plant. The mass, the volume, the power requirements, the chemical inputs, and the expertise required to operate it are beyond anything that could be accommodated aboard a vessel that must also carry people, food systems, life support, and propulsion. The ship can carry stockpiles of replacement chips. It can carry cold spares shielded in the most protected sections of the hull. But it cannot make new ones. This means that the ship's electronic systems have a hard ceiling on their operational lifespan. When the last functional chip for a critical system fails, and the last spare has already been installed, and the crew has no way to fabricate a replacement, that system dies permanently. If the system was controlling the air recycler stops responding to automated commands. If it was managing the reactor's control rods, the reactor loses fine-grained power regulation. If it was processing navigation data, the ship loses the ability to know precisely where it is or where it is heading. Not every system requires the most advanced chips. Some functions can be performed by simpler electronics that might be fabricable in a shipboard workshop using cruder lithography or even hand-assembled discrete components. Analog circuits, relay-based controls, and mechanical backup systems could substitute for digital automation in some areas. But each substitution comes with a cost in precision, speed, reliability, and capability. The ship would be voluntarily regressing its own technological level to stay alive. It would trade sophistication for survival, accepting worse performance in exchange for continued operation. Semiconductors are the most dramatic example, but they are not the only irreplaceable technology aboard. Specialized alloys used in reactor vessels and high-temperature turbine components require precise metallurgical processes that depend on controlled atmospheres, specific temperature profiles, and rare elemental additives. High-precision optical components for telescopes, spectrometers, and medical imaging systems require polishing and coating techniques that are difficult to replicate outside a dedicated laboratory. Certain pharmaceutical compounds require synthesis pathways that depend on precursor chemicals with limited shelf life. Each of these represents a category of technology where the ship's ability to manufacture replacements is either severely limited or non-existent. The crew can improvise, they can adapt, they can find workarounds. Human ingenuity is remarkable, and the history of spaceflight is full of examples where creative problem solving saved missions from seemingly hopeless equipment failures. But improvisation works best against individual, isolated failures. It works less well against the slow, broad, simultaneous degradation of dozens of systems across multiple technological domains. Eventually, the improvisations start requiring components that themselves need improvising, and the chain of workarounds becomes so long and so fragile that a single additional failure can unravel multiple systems at once. Medicine sharpens this problem to a fine edge. A colony ship cannot carry a full hospital. It can carry a well-equipped medical bay with surgical tools, imaging equipment, a pharmacy, and diagnostic instruments. But every item in that bay has a lifespan. Pharmaceutical drugs degrade. The active compounds break down through hydrolysis, oxidation, and photochemical reactions. Studies of drug stability in space have shown that some medications lose significant potency within 1 to 2 years, and the shelf life of the overall pharmaceutical supply depends heavily on storage conditions that must be maintained continuously. Surgical capability is limited by the available expertise and equipment. A ship carrying 10,000 people might include several trained surgeons at departure, but surgery in reduced gravity is largely untested. Blood behaves differently without full gravity. Fluids do not drain naturally from a wound site. Anesthesia delivery and monitoring must account for altered physiology. And the surgical tools themselves are precision instruments that cannot be easily replaced when they wear or break. Beyond acute surgical care, there is the entire domain of chronic medicine. Dental care requires specialized tools and materials that degrade over time. Vision correction requires lenses that must be ground to precise prescriptions. Prosthetics and implants require materials and fabrication techniques that may exceed shipboard manufacturing capability. Mental health care requires trained practitioners whose expertise must be transmitted to successors across generations without the institutional infrastructure of universities, residency programs, or supervised clinical practice. A single generation that produces no competent psychiatrists leaves the next generation without mental health support during what may be the most psychologically demanding living conditions in human history. The deeper medical challenge is generational. The first generation of colonists was selected and screened on Earth. They were chosen for health, resilience, and genetic fitness. Their children, born aboard the ship, were not selected. They carry whatever genetic variants their parents passed on, including recessive alleles for diseases that might not manifest for several generations. Without the diagnostic and therapeutic infrastructure of a planetary medical system, conditions that are manageable on Earth become potentially devastating aboard a closed vessel. An epidemic represents the extreme case. A novel pathogen, whether mutated from the ship's own microbial community or arising from contamination of the agricultural system, could spread through the enclosed population with a speed and severity that no shipboard medical facility could contain. Quarantine aboard a pressurized vessel with shared atmospheric systems is extraordinarily difficult. Every corridor, every ventilation duct, every common space becomes a potential transmission pathway. On Earth, epidemics are terrible, but survivable, because the population is dispersed, medical resources can be mobilized from unaffected regions, and the sheer size of the species provides a buffer. On a colony ship, the population is the buffer, and it is measured in thousands, not billions. Population genetics introduces a threat that operates on the longest timescale of all, and it is the one most people never consider. Every human population carries a load of harmful, recessive alleles, genetic variants that cause no problems when only one copy is present, but produce disease or disability when an individual inherits two copies, one from each parent. In a large, diverse population, the odds of two carriers of the same rare recessive allele having children together are low. In a small, isolated population with no influx of new genetic material, those odds rise with every generation. Cousins marry, second cousins marry. Within a few generations, the probability that any given child inherits two copies of a harmful allele increases dramatically. The population begins to sicken from within. Anthropologist Cameron Smith published an analysis in 2014 arguing that an interstellar generation ship would need a founding population of between 10,000 and 40,000 people to maintain sufficient genetic diversity over a multi-century voyage. His reasoning accounted not only for the raw number of genetic variants needed to avoid inbreeding depression, but also for the cultural diversity, skill redundancy, and adaptive variance required for a population to remain resilient across generations in an unpredictable environment. Other researchers have used the conservation biology framework known as the 50 and 500 rule, which holds that a minimum effective population of roughly 50 individuals is needed to avoid severe inbreeding depression in the short term, and roughly 500 is needed to maintain enough genetic diversity for long-term survival. But effective population size is not the same as census population size. Not everyone reproduces equally. Random fluctuations in birth rates, sex ratios, and fertility can reduce the effective population below the census count by a significant margin. If the colony ship's population drops below the minimum viable threshold, whether through epidemic, accident, infertility, or simple demographic bad luck, the genetic consequences are irreversible. Inbreeding depression manifests as increased rates of genetic disease, reduced fertility, lower immune function, and decreased overall fitness. These effects do not appear immediately. They accumulate across generations, becoming more severe with each cycle of reduced diversity. By the time the symptoms are visible in the population, the genetic damage may be too deep to correct without outside genetic material, which does not exist aboard the ship. Managed breeding programs, embryo banks, and genetic screening can mitigate this risk, but cannot eliminate it. They require infrastructure, expertise, and social cooperation that must be maintained across generations. And they introduce their own ethical and governance challenges that no human society has ever had to navigate. Governance is the final layer, and it may be the most unpredictable. Every isolated human community ever studied has experienced psychological deterioration, social fracturing, and leadership crises under conditions far less extreme than those aboard a colony ship. Antarctic research stations, which house small teams for periods of 6 to 12 months, routinely document what psychologists call the third quarter phenomenon, a measurable decline in mood, motivation, interpersonal cohesion, and cognitive performance that clusters around the midpoint and later phases of the isolation period. Crew members become irritable. Conflicts that were manageable in the early months escalate. Sleep quality deteriorates. Depression and anxiety increase. The Mars 500 experiment, which confined 6 men in a 550 cubic meter chamber for 520 days to simulate a Mars mission, observed substantial individual differences in psychological response, but confirmed that prolonged confinement produces behavioral changes that are difficult to predict and difficult to mitigate even with advanced preparation. And these are volunteers who chose the assignment, who can communicate with family on Earth, and who know that their confinement will end on a specific date. The crew of a colony ship has none of those comforts. They cannot leave. They cannot call for help. For a generation ship, the people born aboard did not volunteer for the mission. They were born into it. They inherited a voyage chosen by ancestors they may never have known, heading toward a destination they may not care about. Confined inside walls they did not build and cannot escape. The psychological and social pressures of that situation are without precedent in human experience. Governance structures must survive the death of their founders. Laws must remain legitimate across generations that had no voice in creating them. Technical knowledge must be transmitted perfectly from one generation to the next, because a single generation that fails to learn how to maintain the reactor, or the water recycler, or the agricultural system could doom every generation that follows. And the social contract that holds the community together must endure stresses that include resource scarcity, medical emergencies, interpersonal conflict, generational resentment, and the fundamental existential burden of living inside a machine with no exit. History offers no example of any human institution maintaining this level of operational and social continuity for more than a few centuries without external contact, new resources, or territorial expansion. Empires rise and fall, religions schism, languages drift, technologies are lost and rediscovered. The colony ship would need to defy every pattern in the historical record, sustaining a culture of precision maintenance, knowledge preservation, cooperative governance, and psychological resilience across a span of time longer than most civilizations have endured on a planet with unlimited air and open sky. All of these threads converge on a single concept that defines the true survival limit of a colony ship: the repair cliff. The repair cliff is not a moment. It is a threshold. It is the point at which the rate of system degradation exceeds the crew's capacity to repair, replace, or work around the failures. Before the cliff, the ship is a functioning world. Systems break, but they are fixed. Components wear out, but they are replaced. Knowledge gaps appear, but they are filled. The crew keeps pace with entropy. The machine stays alive. After the cliff, the balance tips. Failures begin accumulating faster than repairs can address them. A pump fails and is replaced, but the replacement was the last spare. And the machine shop cannot fabricate a new one because the lathe bearing is worn, and the replacement bearing requires a grade of steel the ship no longer has in stock. A circuit board degrades beyond correction, and the backup board was damaged in storage by radiation exposure that the shielding could not fully block. A section of hull develops a slow leak that is repaired, but the welding equipment used for the repair is itself approaching end of life, and the next repair will have to be done with a less capable tool. Each fix costs more effort, more material, and more time than the last, while the failures continue arriving at the same relentless pace. The colony does not die in a single catastrophic event. It enters a slow decline. A system that once ran at full specification now runs at 90%. A component that once lasted 10 years now lasts 6. A repair that once took an afternoon now takes a week because the tools are worn and the technician is less experienced than the one who retired. The degradation is not confined to one domain. It touches everything simultaneously, because everything aboard the ship is connected to everything else, and the decline in any one system quietly accelerates the decline in the systems depending on it. Each individual degradation is manageable, none of them is immediately fatal, but they compound. The slightly worse air quality reduces the crew's cognitive performance. The reduced cognitive performance leads to slower and less precise maintenance work. The less precise maintenance leads to slightly worse repairs. The worse repairs lead to faster subsequent failures. A feedback loop forms, so gradual that no single day feels like a crisis, but so persistent that the trajectory becomes unmistakable over years. This is the repair cliff, not a wall the ship hits, a slope it slides down. The gradient is gentle at first. The crew compensates. They work harder. They get creative. They accept lower standards where they must and hold the line where they can. But the slope does not flatten. It steepens. And at some point, the crew's ability to hold the line is exceeded by the rate at which the line moves. The stored supplies are the buffer. They buy time on the slope. Every spare part in the inventory is a step that the crew does not have to descend today. Every backup system, every reserve of raw material, every extra tool is a delay between the present and the cliff's edge. But buffers are consumed. Delays expire. And unless the ship can genuinely manufacture everything it needs from the raw materials aboard, using tools it can maintain, guided by knowledge it can preserve, the cliff is not a possibility. It is a destination. The ship does not stop being a ship when it crosses the repair cliff. Its hull remains intact. Its mass continues through space on whatever trajectory it was following. From the outside, nothing appears to change. But inside, the world is contracting. Systems that once maintained themselves are now maintained by diminishing resources. Functions that were automatic become manual. Functions that were manual become impossible. The population that once lived inside a technological civilization begins living inside the remnants of one. The ship keeps moving. The colony stops growing. And the question of how long a colony ship could survive becomes a question that requires not one answer but many. Because every system aboard has its own timeline, its own failure curve, and its own relationship to the repair cliff. The air recycler might last 30 years, the reactor might last 60, the hull might hold for a century, the genetic diversity might hold for 5 generations, the social structure might hold for 3, the semiconductor inventory might be exhausted in 40 years. The ship survives as long as all of those timelines overlap. The moment any single irreplaceable system crosses its cliff, the countdown enters a new phase. And when you stack those timelines on top of each other and trace them forward through months, years, decades, and centuries, a picture emerges that is both remarkable in its ambition and sobering in its fragility. A picture that finally answers the question this story set out to ask. So, how long could a colony ship actually survive in deep space? The question sounds like it should have one answer. A number, 50 years, 200 years, 1,000. But the reality revealed by everything we have examined is that the question cannot be answered with a single figure, because a colony ship does not have one lifespan. It has dozens. Every system aboard follows its own failure curve. Every component degrades on its own timeline, and the ship remains viable only for as long as all of those timelines overlap. The moment any critical system crosses the threshold where it can no longer be maintained, the entire architecture of survival begins to contract. What follows is not a prediction. It is a projection, grounded in what we know from existing space systems, closed ecosystem experiments, material science, population genetics, and the operational histories of the most isolated human communities ever sustained. It walks through the life of a colony ship in stages, not because the boundaries between stages are sharp, but because the nature of the challenges changes as the years accumulate. The first phase is measured in months to roughly 5 years. Call it the honeymoon. During this window, the ship operates almost exactly as designed. Every system is new or nearly new. The air recyclers run at peak efficiency. The water recovery rate holds at or near its design specification. The food stores are fresh, supplemented by the first harvest from the agricultural bays. The reactor hums at its rated output. The hull is strong. The shielding is intact. The electronics are well within their radiation tolerance. The crew is the crew that was selected, trained, and prepared for the mission. They know the systems intimately. Morale is high, sustained by the sense of purpose and the novelty of the undertaking. Problems during this phase are small and solvable. A clogged filter is replaced from inventory. A software glitch is patched. A malfunctioning sensor is swapped out. The maintenance burden is light, and the crew has ample reserves of time, material, and expertise to handle whatever arises. The systems work. The food grows, the water flows, the air is clean. This is the phase the colony ship advocates most often describe, and it is real. A well-designed colony ship could almost certainly sustain its population through the first several years of a voyage. The challenge was never the first phase. The challenge is everything that comes after. The second phase stretches from roughly 5 years to 20 years. Call it the first test. During this window, the ship transitions from consuming its initial reserves to depending on its regenerative systems. Stored food supplies that supplemented the agricultural output begin to run low and must be phased out entirely. The crops must now provide the full caloric and nutritional needs of the population, and any shortfall becomes an immediate dietary crisis rather than a minor inconvenience offset by opening another crate. Mechanical wear becomes visible and persistent. The first major component replacements are required. Pump impellers that were designed for a 10-year service life reach end of life and must be swapped. Filter membranes in the water recycling system lose efficiency and must be changed more frequently than projected, because the actual chemistry of the recycled water diverged slightly from the laboratory conditions under which the membranes were tested. Seals in the atmospheric containment system begin to harden, and the leak rate, the rate at which air slowly escapes through microscopic gaps in the pressure boundary, begins to creep upward. The crew starts drawing on its spare parts inventory in earnest. If the inventory was well planned and the failure rates match projections, this is manageable. If not, the first difficult choices emerge. Do we use the last replacement membrane now, or do we stretch the current one another 6 months and accept a slight decline in water quality? Do we replace the bearing in the ventilation fan motor today, or do we wait until the vibration becomes audible and risk a catastrophic seizure that could take the entire airflow system offline? Pharmaceutical supplies begin to degrade. Medications that were effective at launch are now several years past their formulation date. Some retain adequate potency, others do not. The medical team begins rationing certain drugs, reserving them for the most critical cases while treating less severe conditions with reduced doses or alternative therapies. The first deaths aboard the ship from causes that would have been treatable on Earth occur quietly, logged in the medical records, mourned by the community, and absorbed into the evolving reality of shipboard life. The psychological texture of the voyage shifts. The novelty is gone. The mission is no longer new. The faces are the same faces. The corridors are the same corridors. The daily routine, which once felt purposeful and exciting, begins to feel like a sentence. The third quarter phenomenon, documented so reliably in Antarctic stations and submarine deployments, does not arrive as a discrete event. It seeps in. Interpersonal tensions that were tolerable in the first years become entrenched grievances. Factions form. The governance structure, whatever form it takes, faces its first serious internal challenge. Someone disagrees with an allocation decision. Someone refuses a work assignment. Someone questions the authority of the leadership to make decisions on behalf of people who did not choose to be here. The second phase is survivable. Many of its challenges are anticipated and planned for. But it is the phase where the gap between design and reality first becomes visible. The systems are no longer performing exactly as specified. The margins are narrower, the buffers are thinner, and the trajectory, for the first time, bends slightly downward. The third phase runs from roughly 20 years to 50 years. Call it the long erosion. This is the phase where the original generation begins to age and die. The engineers who built the ship, the doctors who stocked the medical bay, the farmers who planted the first crops, the leaders who designed the governance system, all of them are growing older. Their knowledge is irreplaceable unless it has been successfully transmitted to the generation behind them. And knowledge transmission across generations, under conditions of extreme isolation and resource constraint, is far harder than it sounds. On Earth, a young engineer learns their trade through years of formal education, supervised practice, exposure to a wide variety of projects, and access to a vast body of recorded knowledge maintained by libraries, universities, and professional institutions. On a colony ship, the educational infrastructure is whatever the crew can maintain. The library is whatever digital and physical records survived the radiation exposure of the first 2 decades. The teachers are the aging first generation who must somehow convey not only the facts and procedures of their specialties, but the intuition, the judgment, the ability to diagnose a problem from subtle cues that comes only from years of hands-on experience. If the transmission is successful, the second generation takes over maintenance of the ship with competence roughly equivalent to the first. If it is incomplete, if even one critical specialty fails to transfer because the expert died before completing the training, or because the student lacked the aptitude, or because the teaching materials were damaged, a permanent gap opens in the ship's capability. A skill lost is a skill that may never be recovered, because there is no one else to learn it from, and no institution to consult. During this phase, the cumulative effects of radiation on both the crew and the electronics become impossible to ignore. Cancer rates in the population are measurably elevated above the terrestrial baseline. The medical system is managing a growing burden of chronic disease with a shrinking inventory of effective pharmaceuticals. Electronic systems that have been operating for 20 to 30 years show calibration drift, increased error rates, and reduced processing speed. The first radiation-hardened components reach end of life and are replaced with spares that are themselves partially degraded from decades of storage under imperfect shielding. The hull shows its age. External inspection, conducted at great risk through extravehicular activity, reveals micrometeorite pitting across the forward surfaces, thinning of protective coatings, and early-stage fatigue cracking at structural joints subjected to the most thermal cycling. The repairs are possible, but costly in time, risk, and material. The ship that was new and strong at launch now requires constant vigilance to keep structurally sound. The agricultural system has drifted from its original design. The soil ecosystem has evolved. Microbial communities that were carefully selected at departure have shifted in composition over 20 years of operation, producing changes in nutrient cycling, pest dynamics, and crop yields that the second-generation agronomists must manage without the baseline data and controlled conditions their predecessors relied on. Crop varieties that performed well in the first decade may be struggling now as the soil chemistry, the light spectrum of aging grow lamps, and the atmospheric composition inside the agricultural bays have all shifted incrementally from their original parameters. Beneath the visible crops, an invisible transformation is underway. The radiation-driven mutations described earlier have had 2 decades to accumulate in the ship's microbial populations. But radiation is only half the pressure. The other half is ecology. In a sealed vessel with no wind carrying fresh spores, no rain washing in new soil bacteria, no migrating animals depositing organic material from distant ecosystems, the microbial community has no source of renewal. It can only work with what it has. And what it has is changing. Species that were dominant at departure have been outcompeted by variants better suited to the ship's altered chemistry and atmosphere. The soil behaves differently now. Nutrient cycles have shifted in ways that the textbooks loaded at launch did not anticipate. Crop diseases appear that the first-generation agronomists never encountered, caused by organisms that did not exist in this form when the voyage began. The crew cannot see any of this at the microbial level. They can only see its effects in falling yields, in unexplained blight, in soil that no longer responds to the treatments that worked 5 years ago. The agricultural bay looks the same. The ecosystem inside it has quietly become something else. The spare parts inventory is noticeably diminished. The machine shop, if one exists, is producing replacement components, but each one is slightly inferior to the factory original part it replaces. Tolerances are wider, materials are substituted. Surface finishes are rougher. The replacements work, but they wear faster, perform less efficiently, and fail sooner than the parts they replaced. The maintenance cycle tightens. More crew time is devoted to keeping systems running. Less time is available for everything else. The fourth phase begins at roughly 50 years and extends to 100. Call it the narrowing. By this point, the original crew is gone. Every person aboard was born on the ship or arrived as a young child. No one remembers Earth from personal experience. The mission's origin story is history, not memory. The ship is not a vessel carrying people from one world to another. It is the world. It is the only world anyone aboard has ever known. The semiconductor inventory is critically depleted. Some electronic systems have already been downgraded to simpler architectures, trading capability for longevity. Functions that were once automated now require manual monitoring. Alarms that once triggered automatic responses now trigger a crew member walking to a panel and reading a gauge. The ship is becoming less intelligent as its electronic nervous system thins. The reactor, if it is a fission design, may be approaching the limits of its fuel supply or its structural integrity. Neutron embrittlement has been accumulating in the reactor vessel for decades, slowly changing the crystalline structure of the metal at the atomic level, making it more brittle and less able to withstand the thermal and pressure stresses of operation. The control systems have been repaired multiple times with components of decreasing sophistication. Safety margins that were once generous have been eroded by successive substitutions and workarounds. The power output may have been deliberately reduced to extend the reactor's remaining life, which means every system aboard is operating on a tighter energy budget. The grow lights are dimmer. The water recyclers run fewer cycles per day. The temperature regulation system allows wider swings between the warm and cool ends of the habitat. The ship feels different now. Not broken, not failing, just slightly diminished in every direction at once, as if the world itself has quietly contracted by a few percent. The population has either remained stable through careful management of birth rates and resource allocation, or it has declined. If it has declined, the genetic diversity of the community is lower than it was at departure. The effects of inbreeding depression may be emerging in the third or fourth generation, manifesting as increased rates of genetic disease, reduced fertility, and lowered immune function. The medical system, already strained by pharmaceutical depletion and equipment aging, faces a patient population that is becoming biologically more vulnerable with each passing decade. Governance has been tested by at least one serious crisis, possibly several. A faction may have attempted to seize control of resources. A dispute over reproduction rights or population policy may have fractured the community. A religious or ideological movement may have emerged among the shipborne generations, reinterpreting the mission's purpose in ways that conflict with the original operational priorities. The social fabric, stretched across 50 years of confinement with no external contact and no escape, shows its strain in ways that the mission planners could not have fully anticipated. The repair cliff is no longer a theoretical threshold. It is now visible in the operational data. The rate of system failures has begun to outpace the rate of successful repairs. The machine shop can still produce some replacement parts, but it cannot produce all of them, and the gap between what it can make and what the ship needs is widening. The crew is working harder than ever, devoting more hours to maintenance, accepting greater risks during repairs, and tolerating lower performance from patch systems. The trajectory is clearly downward. The only question is how steep the slope becomes. Beyond 100 years, the picture becomes speculative, because no human institution has ever operated under these conditions for that duration. But the trajectory points in one direction. A colony ship that reaches the century mark has accomplished something unprecedented in human history. It has sustained a closed artificial biosphere, powered by a single energy source, maintained by a population with no external support, through a span of time longer than most nations have existed. That achievement would be extraordinary regardless of what follows. But the physics and the biology do not pause to celebrate milestones. They do not recognize the significance of what has been accomplished. They operate with the same indifference on day 36,500 as they did on day 1. The processes that have been degrading the ship for 100 years continue. The hull is thinner. The reactor is older. The electronics are simpler. The population is smaller, or genetically narrower, or both. The knowledge base has contracted as specialties were lost and not replaced. The agricultural system is producing less food from soil that has been recycled thousands of times through a microbial ecosystem that no longer resembles the one that was loaded at departure. At some point, and the exact timing depends on the quality of the ship's design, the size of its initial reserves, the skill of its crew, and a measure of luck, the repair cliff becomes a wall. The last spare for a critical system is consumed. The last functioning unit of an irreplaceable technology fails. The last person who understood how to maintain a particular subsystem dies without a successor. The loop that was already fraying finally breaks. The air recycler cannot maintain the correct atmospheric balance. The oxygen concentration drops by a fraction of a percent per year. Not enough to notice immediately, not enough to trigger an alarm, but enough that, over a decade, the crew is breathing air that is immeasurably thinner than what their grandparents breathed. Cognitive function declines. Physical endurance drops. The work of maintaining the ship becomes harder precisely when the ship needs more maintenance than ever. The water recycler loses another fraction of a percent of efficiency. The total water inventory shrinks, rationing tightens. Crops that required a specific irrigation volume receive less. Yields drop. The caloric output of the agricultural system falls below the population's minimum requirement by a margin so small it is measured in handfuls of grain per day. But it is a deficit. And deficits compound. The reactor produces less power. The temperature regulation system allows the habitat to cool by another degree. Then another. The crew wears more clothing. They eat slightly less. They work slightly slower. They fix slightly fewer things. The slope steepens. The people still living aboard the ship do not experience this as a graph trending downward. They experience it as a world that is slowly, quietly becoming less. The corridors are dimmer than they were when the older residents were children. Not dark, just dimmer. The hum of the ventilation system, which was once a constant background presence as reliable as wind, has developed a faint unevenness. A rhythmic hesitation that no one can quite fix, but everyone has learned to ignore. The food tastes different now. Not because the recipe's changed, but because the soil has changed, and the water has changed. And the trace minerals that gave the wheat its flavor 20 years ago are no longer present in the same concentrations. The medical bay has a cabinet that no one opens anymore because the equipment inside it cannot be repaired. And looking at it only reminds the crew of capabilities they once had and no longer do. There are rooms in the ship that have been sealed off. Not because they are dangerous, but because the systems inside them failed and the resources needed to restore them were redirected to keeping more critical sections alive. The world is not collapsing. It is shrinking. And the people inside it adjust to each small subtraction the way people always do, by forgetting what they used to have. This is not a dramatic ending. There is no explosion. There is no collision with an unseen object. There is no alien encounter, no mutiny that vents the atmosphere, no single moment where the lights go out and the screen goes dark. The colony does not die the way colonies die in fiction. It thins. It fades. It contracts inward, system by system, capability by capability, until the gap between what the ship needs to remain livable and what the crew can provide becomes too wide to bridge. The whole remains intact. The ship continues on its trajectory, obedient to Newton's first law, moving through the interstellar void at whatever velocity it reached during its acceleration phase. From the outside, if anyone were watching, it would look no different than it did on the day it launched. a metal cylinder gleaming faintly in the light of distant stars, drifting in silence through the deepest emptiness the universe contains. But inside, the world has ended. Not with fire, with wear. And this is the truth about a colony ship that sits at the center of every calculation, every engineering study, every population model, and every thought experiment ever conducted on the subject. The terrifying part is not that it would fail. Failure is expected. Everything built by human hands eventually fails. The terrifying part is the gap between the death of the colony and the death of the ship, because the ship can outlast its inhabitants by millennia. A pressurized hole in interstellar space, with no atmosphere to corrode it and no weather to erode it, could maintain structural integrity for thousands of years. The vacuum outside preserves. The cold outside stabilizes. The very emptiness that made the voyage so hostile to life makes it remarkably gentle on inert metal. The ship drifts on, intact, silent, and empty, long after the last crop failed, the last recycler stopped, and the last person aboard drew their final breath in a room that was slightly too cold and slightly too thin of air. It becomes an artifact, a monument to an attempt so ambitious that the species that built it did not yet possess the ability to sustain it. A sealed world that kept its promise for decades, perhaps for a century, perhaps even longer, before the accumulated weight of entropy, biology, and isolation slowly closed it down. There is a version of this story that ends with hope. In that version, the colony ship does reach its destination. The crew, battered and diminished but alive, enters orbit around a new world and begins the process of rebuilding everything they lost during the voyage. Their children descend to the surface and breathe unrecycled air for the first time in generations. The colony takes root. Humanity spreads. The ship is remembered as the vessel that carried the species across the void. That outcome is not impossible. It is not ruled out by the laws of physics. A sufficiently advanced ship, with a sufficiently large and capable founding population, traveling a sufficiently short distance to a sufficiently hospitable destination, might arrive with enough people, knowledge, and equipment to begin again. The margins would be razor thin. The risk at every stage would be enormous. But it is merely the hardest thing the human species has ever contemplated doing. And there is a version of this story that does not end at all. In that version, the destination was always too far away. The colony endures for as long as it can, maintaining its systems with decreasing effectiveness, watching its capabilities contract year by year until it crosses the repair cliff and begins its long, slow descent toward uninhabitability. In that version, the ship was never transportation. It was always an experiment in whether a closed human civilization could outlast the machinery keeping it alive. The evidence from every source examined in this story converges on a single conclusion. A colony ship could survive in deep space for a meaningful period. With excellent engineering, vast reserves, a large and genetically diverse population, a culture of meticulous maintenance, and a measure of good fortune, that period could extend to decades. Under the most optimistic assumptions, it might stretch to a century or more, but survival and sustainability are not the same thing. The ship survives as long as its stored reserves and initial equipment hold out. It becomes sustainable only if it can manufacture, repair, and reproduce every system keeping it alive, using only the materials and knowledge aboard, indefinitely. No closed system in human history has achieved that. Not Biosphere 2, not the space station, not any submarine, Antarctic base, or sealed habitat ever constructed. The loop has never been fully closed. A colony ship is not merely a vehicle. It is a civilization compressed into a container, hurtling through an environment that erodes the container and weakens the civilization inside it simultaneously. It is a world without a sky, without weather, without seasons, without horizons. It is a world where every breath is manufactured, every drop of water is recycled, every calorie is grown under artificial light, and every mechanical heartbeat depends on a chain of repairs that stretches backward through every tool, every spare, every skill, and every irreplaceable component the ship carries. The ship's greatest enemy is not a collision. It is not a reactor meltdown. It is not a mutiny or a plague. It is time. Time working through radiation on electronics. Time working through fatigue on metals. Time working through degradation on seals, coatings, and polymers. Time working through loss on knowledge, skills, and genetic diversity. Time working through entropy on every closed loop the ship depends on to stay alive. Not one catastrophe. 1,000 tiny subtractions, each one invisible on its own, each one compounding every other, until the sum is larger than the whole can bear. And the deepest irony is this: the same emptiness that threatens the colony is what preserves the ship. Deep space has no oxygen to rust the hull, no rain to corrode the surface, no microbes to consume the structure, no gravity to stress the frame. The ship, as a physical object, could endure for tens of thousands of years in the interstellar void, drifting in perfect preservation through the dark between the stars. The colony inside it could not. The ship outlives its builders. That is the image that stays. A metal world, still pressurized, still airtight, still carrying the residue of everything a civilization needed to live. Seeds that will never germinate, tools that will never be lifted, books that will never be read, medical instruments that will never touch a patient, an agricultural bay with soil that once grew wheat under lights, that once shone with the energy of a reactor, that once burned with the fuel, that a species on a distant planet once refined from ore, they pulled from the ground of the only world they had ever known. The ship keeps moving. It will keep moving for millions of years unless something stops it. It will cross the distance between stars. It will pass through regions of the galaxy that no human eye has ever seen. And it will carry, sealed inside its silent hull, the evidence that a species once looked up at the night sky and decided that the distance was not too far, the risk was not too great, and the darkness was not too deep to try. A colony ship is humanity's most ambitious escape plan. It is also the most fragile world we could ever build. And the answer to how long it could survive is not a number. It is a question thrown back at the species that dares to ask it. How much can you carry? How well can you build? How carefully can you maintain what you have? How faithfully can you pass your knowledge to your children? And how long can you hold a world together when the universe offers nothing but patience and silence and cold? The ship does not answer. It just keeps moving. Through the dark, through the silence, through the space between the stars that stretches out ahead of it like a question that may never be answered. And maybe that is enough. Not the arrival, not the destination. Just the fact that someone built it. Someone boarded it. Someone believed that a sealed metal world, carrying everything a species needs to survive, could cross the emptiness and emerge on the other side still breathing, still thinking, still alive. Whether it could is a question for engineers and physicists and geneticists. Whether it should is a question for all of us. And the distance between those two questions is the distance the colony ship was always trying to cross